Okay, so let's make a start. So where have we reached? So we're still on chapter 1, but part 2. That's the second set of notes, excuse me. Page 230, the law of total probability. So before we get into the lecture, just to let you know, for those of you who are taking the midterm, that it's looking very likely that the midterm will be on Tuesday, March the 12th at 8 p.m. We do appreciate that some people will still have a clash, but there's such a huge class we can't avoid it, so there will be a make-up for anyone who can't make that date. But that's not confirmed yet. We're still waiting on the room, but it's looking likely like that date. Okay, so we're on page 230, the law of total probability. So what are the things that we've been looking at? Sorry, it's a long way. What have we been looking at? So the main thing that we were investigating towards the end of last week's lecture was this notion of a conditional probability. Sorry, I find the formula somewhere. So remember, the idea was that we were interested in a probability of a set B or an event B, and we know the event A has already occurred. So remember that was defined for all sets A with positive probability, that the probability that B occurs, given that A has already occurred, as the probability of A and B over the probability of A. And we spent a long time investigating this and looking at multiple versions of that and so on and so forth. Okay, so that's moved us on to this new concept of the law of total probability. And actually, it's a kind of nice precursor for doing things properly, if you like, with random variables. So sets are kind of like the simple way to do everything, but we're going to move to some quantities which are not sets, which are called random variables. And this is basically called a marginalization law, but we'll learn that later on. Let's take this setting. So the idea, we have a collection of n sets, A1, A2, up to AN. They form a partition. Remember, that means that for any pair I and J, AI, AJ, where I is not equal to J, the intersection is empty, but if I take the union of those sets, I get back the entire sample space. That's what this is. That's the partition. Then the result that we're going to quote, this is the law of total probability, the theorem of total probability, if you like, and it says the following: I take any event B, right, whatever I like. Now, if I want to compute the probability of B, that is equivalent to taking the sum over all i's of the intersection of B with AI, okay? Or if you prefer, as we know, if the probability of the AI's are strictly positive, this conditional probability is well defined, so this intersection is precisely equal to this product, precisely by the definition of the law of conditional probability. Okay, and that's the law of total probability. Okay, there is no, well, one can prove this result, but it's not important for this course. Okay, you can take it as a law, right? So what does this mean? So this diagram has some typos in it. So here the roles of A and B are reversed. So here I'm interested in the probability that A occurs. So here it was B, and here AI's form the partition, but in this example the B's form the partition. Okay, so what this basically means is, so A is this red circle, the event of interest, and I'm saying the probability of the A occurring, if I take a partition, so this is B1, B2, B3, so the B1, B2, let's call that B3, B4, and B5, okay, then the probability A occurs is simply the probability of this intersection plus the probability of this intersection plus the probability of this intersection plus the probability of this intersection, okay? So you're just adding up the red shaded regions to give us the probability of A if the total mass of that square is rectangle is 1, and these are all numbers between 0 and 1. Okay, so that's a graphical representation, or not a proof of the result. I mean, it's just to try to help you believe that this result that I'm quoting here is true. Okay, it's a result we're going to use frequently, and there are many important generalizations of this result, so we need to understand this from the beginning. Okay, there's a lot of examples here. This whole class seems to be examples this today. Which is no bad thing, so we can try to understand this concept from the beginning. So example 1, so we have a certain factory, and there are three machines, A, B, and C, and they produce, they're producing presumably screws, and 2%, 1%, and 3% respectively are defective. Okay. On total production, okay, machines A, B, and Z produce 35, 40, 25, and 60%, 40% respectively. That is to say that these machines, they produce screws. I take out 35% of them, and they will be from A, 25% will be from B, and 40 will be from C. And we are asked two questions. A, what is the probability? So I draw, so I have all the, on a given day, let's say, I have all the screws that have been developed by this particular factory with these machines A, B, and C. I put my hand in this massive bucket of screws. I take one out, and I'm asked the question, what's the probability it's defective? And I'm also asked the question, what is the probability that it is produced by machine C, given that it's defective? Okay, so let's start with A, and then I'll read B again so that we'll understand. So let's introduce some notations. So I'm reading from the top. So we let D be the event that the defective screw is selected. Okay, A, defective screw is selected. And A, B, and C are the event that the selected screw comes from machines A, B, and C respectively. Okay, so this is these A, B, and C are mutually exclusive. So we note that if we interpret these as probabilities, that the sum of these as interpreted as probabilities is 1. So basically, if I select a screw, it must come from A, B, or C. So that partitions the whole sample space of screws, if you like. So that's what it says here. A, B, C are mutually exclusive events, and they partition, of course, they partition the space, right? So now what we're asked in part A, what is the probability that the screw randomly selected is defective? So we're going to apply the law of total probability. So we know precisely from our law of total probability that the probability that D occurs, so I'm simply applying this result here where this B is represented by D in our example, and these AIs are A, B, and C respectively. So our partition number N is 3. This is true for any finite fixed N, by the way. N could be 2, it could be 25, okay, as an example. So the probability that D, the screw is defective, is simply the probability that the screw is defective given that it's from machine A, multiplied by the probability it's from machine A, and so the same for B and C, respectively. So for A, the probability that the screw comes from machine A is 0.35. Okay, that's that number there. The probability that it's defective given it's from machine A, well, that's 0.02. That's what that number is there. Okay, similarly, if I look at this one, the probability that the screw comes from machine C is 0.4. The probability that the screw is defective given that it comes from machine C is 0.03. Okay, so then I plug all those numbers into the formula. You could do the same for B, add them up, and I get 0.0215. Okay, now question B, so let's repeat that so that we're clear. So what's the probability that the screw that I have selected is from machine C, given that I know it's defective? So I put my hand in this bucket of screws, I've taken one out, okay, I say, okay, it's defective. Now I know it's defective, but I want to know whether or not it's from machine C. Now I don't know that for sure, unless someone can tell me, but I can work out what the probability of it is occurring. Okay, so this is a conditional probability. The probability that the screw is from machine C, given that it's defective, and that's simply by the law of the definition of conditional probability. So that's the thing that I quoted right at the beginning of the lecture. That's the probability that C occurs and D occurs simultaneously, divided by the probability that D occurs. Okay, well, I know the probability that D occurs, that's what I just computed at part A. Now, the probability that C and D is the probability of D given C times the probability of C. Okay, that's just using the rearrangement of the probability, conditional probability rule. So this, given this, is the probability of C and D over the probability of C. Okay, now, the probability that they're defective, given that it's come from machine C, well, this number is 0.03. The probability it comes from machine C is 0.4. So I plug those numbers in. There's this one, and this one here, and I get 0.5581. Actually, this example is interesting because this has derived a very famous result. So this line here, which looks innocent and is something that we're going to investigate towards the end of the lecture today, or certainly by tomorrow, is something called Bayes' theorem. And I'll explain the intuition for it. But this is a simple conditional probability statement. So this says that the probability of C given D is precisely like this. Okay, and there is an interpretation of this in statistics and probability, which I don't know if we have time we'll discuss today. Okay, anyway, let's go back on to our example. So example 2, so we're still doing the law of total probability. We have a bag, it contains 4 white balls and 3 black balls, and a second bag which contains 3 white balls and 5 black balls. Okay, very good. So this is the procedure that we're going to have. So one ball is taken from the first bag and placed unseen into the second bag. So I take it could be white or black, I don't know what it is, I put it in the second one. I don't know what color it was. Now we're asked the question, what is the probability that a ball now drawn from the second bag is black? Okay. So let's formulate this problem. So there's actually a slight typo in this solution, which I will point out as we go along. So we define A1, which is the event that the first ball that is drawn is white. And A2 is, of course, the complement of A1, which is that the first ball drawn is black. And B is the ball drawn from the second bag is black. Okay, and we're going to work out the probability of B. That's what we want. Now, the probability of A1, which is the probability that the first ball is drawn is white. So we have 4 balls which are white, 3 balls which are black, 7 balls. So the chance that I choose a black ball is 4/7, and the chance that I choose a blue ball is 3/7, because basically I'm doing this randomly. Okay? So that's what that thing says here. Okay? Very good. So I have that, but that's not what I want. I want the probability of B. Now, this one is not quite right. So this says there are 5 white balls among 9 balls in the second bag after the first white ball was drawn. Is clearly not nonsense. So what I'm doing here is I'm thinking about the event A1. Okay, so A1, the first ball is drawn is white. So I take it at the first bag, I take out a ball that happens to be white, I put it in the second one. Now when I do that, what happens in this second one is I now have 4 white balls and 5 black balls. So 9 balls and 5 of them are black. So this statement is correct. The probability that I draw a black ball given the first one drawn was white is indeed 5/9. This statement is not right. There are 5 black balls among 9 balls in the second bag after a white ball, right? So this is a black, not white. Okay, so that's 5/9. So similarly in the second case, I draw a black ball. So what that means is now I've taken one of these, it's a black ball, I put it in here. So now I have 6 black balls, 3 white balls. Now the chance I draw a black ball in this situation is going to be 6/9 because there are 6 black balls and 3 white balls. Okay, that's what it says here. Okay, and now I'm pretty much done because now A1 and A2 partition the sample space, right? I mean, I either pick a black ball or a white ball in my first trial. So now the probability that I'd select B by the law of total probability, which is now n is 2, is the probability of B given A1 times the probability of A1 plus the probability of A2 times the probability of B given A2. These 2 numbers we've computed, these are 2 numbers we've computed. We plug them into the formula and we get 38/63. Okay, I mean, I didn't check this number on it. This one is right. Okay, example 3. So this is just a lot of words, but it's not so complicated once one formulates the problem. So you're given traffic police, and they plan to enforce a speed limit by using cameras at 4 different locations. Okay, that's the first sentence. The speed cameras at each of these locations, 1 to 4, are operated 40, 30, 20, and 30% of the time. That adds up to 100%. Now, if a driver who is speeding on his or her way to work has probabilities 0.2, 0.1, 0.5, and 0.2 of passing through these locations, we're asked 2 questions. We'll start with the first one because otherwise we will forget B. So let's just think about A. So what's the chance that that individual receives a speeding ticket? So there's a lot of words here, but let's try and formulate it. And we'll do part A and then we'll come back to B. So let's investigate this problem. So we define, first of all, the event that the driver receives a speeding ticket. So that's what I want to compute the probability of B. And now I introduce this notation AI, that this individual passes through the location Li. Okay, location 1, 2, 3, 4. I is in set 1 to 4. Okay, and so now what I want to do is I want to compute the probability of B. Now this individual is going to pass through the location 1, 2, 3, or 4. Okay, and this is 0.2 plus 0.2 plus 0.1 plus 0.5 is 1. So that partitions the state space, the probabilities. Okay, so this is the probability that of B given A1, given A times A1, B given A2 plus A2, and so on and so forth. Right, that's just using the law of total probability in the case n is equal to 4. Now, what are these numbers? First of all, the probability that that individual passes through location 1 is 0.2. Okay, that's that thing. And then the probability that he receives a speeding ticket given that he passes through location A1 is speed cameras addition. This is 0.4. Okay, 0.4, which is so basically so there's something implicit in this question, which is basically that if the speed camera catches you, if it's operating, then you get the speeding ticket. It's actually it's not obvious, actually. I wouldn't phrase a question like that. So that's 0.4. So for example, now in this second location, the probability that the individual passes through location 2 is 0.1. That's 0.1 there. The probability that that individual gets a speeding ticket given that they pass through A2 is defined to be 0.3, and so on and so forth. So then you multiply those numbers, add them up, and you get 0.27. Part B. So part B now asks the question that that individual passes through the radar trap at location 2 if you receive a speeding ticket. So now we know that the event B has occurred, and we want to find the probability of A2, right? That's what we want. I want to compute the probability of A2 given B. And again, we use the formula for conditional probability. We know the probability of B is positive, by the way. So that's the probability of A2 and B divided by the probability of B. That's the definition of conditional probability. Now, we don't know this event, or we don't know the probability of this event a priori, but we know, again, using the same trick as we did in example 2, I guess, or example 1, I forget which, that upper red, the probability on the right-hand side of the numerator is precisely equal to the shaded term exactly by the law of conditional, the definition for conditional probabilities. Now this probability of B I know. The probability of A2 I know, it's this one, it's 0.1. The probability of B given A2 is 0.3, I know that one. So this solution is 0.1 times 0.3 divided by 0.27 is 1 over 9. Okay, so it's another example. There's a lot of examples. I think that hopefully you understand this concept quite well at the end. Sorry. Okay, so example 4. So a bag contains a 50 cent, a 20 cent, and a 10 cent coin. Okay, just one of each. Now the 10 cent coin actually is a fake. It has 2 heads on it. Okay, very good. Now, what do you do? Now this experiment consists of the following. I choose a coin at random, okay, and I flip it 4 times. Now, if the result is 4 heads, what's the chance that that fake coin, 10 cent coin, is the one I drew? Okay, and you would think it's pretty high a priori, right? Okay, let's think about this. So, let's define 3 events, A, B, C, which is that I choose the 10, 50, and 20 cent, or 10, 20, and 50 cent respectively, and 4H is the event of obtaining 4 heads. So now, what I want to do, if I choose the 10 cent coin, right, so the probability of 4H, actually, this is not very good, this one, the probability of obtaining 4 heads given that I choose the 10 cent coin is exactly 1. Why is that? Well, that's because if I get the 10 cent coin, whatever direction it lands on when I flip it, it's going to be heads. So if I do that 4 times, there's no chance to get anything else, right? I don't like this upper statement. This one does not make sense. This is the one I want, okay? If I choose the 20 cent coin, then the probability of heads is a half, right? So the probability if I flip the coin, it's a fair coin, I get heads or tails, okay? And it so happens the chance of getting 4 heads in a row, you can check there are 4 times, so there's only, so if I do that, so basically I've got 4 possible outcomes of that occurring. So that's going to be 1 over 16. That's the chance of getting 4 consecutive heads. And that's the same when you use the coin C. Okay, so these 2 probabilities are the chance of getting 4 consecutive heads when you have coin B or coin C. So now what do I want to compute? I want to compute the probability of 4 heads, but I still don't know the probability of choosing A, B, or C. Well, I'm choosing them at random, right? So this says I choose the coin at random. There are 3 coins, so I have equal probability of choosing either of those 3 coins. So the probability that I choose a coin A, B, or C is a third, respectively. So now what do I want to do? First of all, I want to compute, what I want to do is I want to compute the probability. What do I want to compute? I want to compute the probability that of A given 4H, okay? And so one way to do that is first of all to compute the probability of 4H and then to use exactly the result that we've been using. So let's first of all compute this, the probability of 4H. So remember A, B, and C partition the state space. I have to choose one of those 3 coins. So this is equal to the probability of 4H given A. Okay, so 4H given A is 1, right? Probability of A is a third, probability of B is a third, probability of 4H given B is a 16th, and then there's a 16th for this one as well. So that's 3/8. So then to compute the probability that I'm asked for, the probability that it's coin A given 4H, and again I expect that to be high, that's equal to the probability of A and 4H over the probability of 4H. Now I've gone to my trouble of computing 4H. Again, using exactly the same trick as in the previous question, the numerator on the right-hand side of the above displayed equation is precisely equal to this highlighted region. So then I've computed this up here, I've computed this up here, and so the required probability is 8 over 9, okay, which is pretty high, right, which makes sense. There's a chance it could have been one of the other coins because basically there is a chance of getting 4 heads with those 2 coins, but that chance is much smaller than when compared to the chance when you have the 10-cent coin because it's 2-headed. So that's why you expect a priori. So if I've got a number here which was like 1/9, I might question my solution because it doesn't make a lot of sense. So very good. So that has led us on to this notion of Bayes' theorem. And Bayes' theorem is actually just a formal statement, essentially, of the results we have used 3 times in the previous examples. So it's a theorem, I mean, it's kind of a theorem, it's a trivial theorem. Let A1 up to AN be a partition of the sample space. This is exactly the same as one has for the law of total probability. So the intersection for any pair AI, for I not equal to j, is precisely empty, and the union of the AIs is precisely equal to the sample space. So then the Bayes' theorem states that the probability that the event AK occurs given B is the probability that AK occurs multiplied by the probability of B given AK over this thing in the denominator, and the denominator you should recognize immediately as being the probability of B. Okay, and this thing is not very difficult to understand because it's basically, this is just like this thing, right? So here you had the probability that the coin was a 10-cent coin given I flipped 4 heads. Okay, that is by definition, so this is basically a proof of Bayes' theorem in a specific case. The general case is very simple to do. That's equal to that by definition for any event 4H which has positive probability. And then I just rearrange this one, again using the law, using the definition of a conditional probability. Okay, now this denominator, remember, it looks like this, and A, B, and C partition the sample space. So this is a kind of proof exactly of this result in the case n is equal to 3. Okay, and it's true for any partition, any fixed n. Okay. Right, in fact it's true for infinite n, but let's not get into that. There is a nice interpretation, so you can look at this. There is a statistical interpretation, which I'll tell you probably, that you may not have heard of, Generally, this interpretation is the following. Sorry, I've lost the page. So this basically, what this corresponds to is the probability that AK occurs before I know B, right? And this is the probability that B occurs given AK. So this is sometimes interpreted as the so-called posterior probability that AK occurs given B. That is to say, if you tell me that B has occurred, given, what is that going on with this? Given that B has occurred, the probability of AK has occurred is given by this formula. So this is like before I see any information, this is some data given the information, and this is the probability of the information given the data. Okay, it's a kind of way of interpreting. If you don't understand what I said, you can just take the formula at face value, right? And we've seen the derivation of that already. So let's have a look at some application of Bayes' theorem. So there are 7 examples here. The last one of which is this. You must have heard of this as the Monty Hall problem. It's very famous. You can see it in many even popular television shows. Actually, I don't like the solution in the example. There are many ways of doing it, and you can learn them yourself. Actually, the solution is not a very good one. Anyway, let's have a look. Example 1. So this first example is the following. You suppose that there is a chance for a newly constructed house to collapse depending on whether or not the design is faulty. Okay? So before I know anything, I know that the chance that the design is faulty is very small. It's 0.01. Actually, I would say it's rather large, but it's 0.01. Now, we're told 2 things. We're told that the chance that the house collapses if the design is faulty. So I tell you the design is faulty, right? The chance it's going to collapse is quite high. It's 0.75. Otherwise, right, if the design is correct, then the chance it falls down is very low. It's 0.0001. And now what happens is the house actually collapses. The question we were asked is, what's the probability that this is due to faulty design? So somehow we're not able to recover that information, although we should be able to in practice. Okay, so this is going to be an application of Bayes' theorem. First of all, we define 2 events, A and B. B is the event that the house's design is faulty, and A is the event that the house collapses. Okay, so we're now told the probability that the design is faulty. That's the first sentence here. The probability that the design is faulty is 0.01. Now, we're told also that the probability that the house collapses given the design is faulty is 0.75. That's like that. And we're also told that if it's not, i.e. if it's properly designed, then it's a very small chance of collapsing. So the probability of A given B complement is 0.0001. Okay, so what do I want to compute? So remember the question asks me, what's the probability that the probability that the design is faulty given that the house collapsed? So in the language that we've written here, I want to compute the probability of B given A. Okay. So let's compute first of all the probability that A occurs. The probability that A occurs is the probability that it occurs given B, i.e. given that the design is faulty, plus the probability times the probability of B, plus the probability A collapses given that the design is not faulty, and this is to be B complement. So this is also a typo. There should be a dash here. Okay, so that, of course, B and B dash are partitioning the sample space. Now the probability of A given B, well, we've got that given here. The probability of B is 0.75. We've got that there. No. Sorry. Probability of B is 0.01. The probability of A given B is 0.75. Excuse me. Okay. The probability of B complement is 0.000. Probability of B, excuse me, is 0.99, and the probability of A given B complement is 0.0001. So this one corresponds to this, and this one corresponds to this. And if you multiply and sum, you get 0.007. So the probability that the design is faulty is exceptionally low. However, now what we're asked to compute is the probability that the design is faulty given that I know that the house collapsed. Okay, so we apply Bayes' theorem. So this is the probability of A occurring, that it is collapsing, given that design is faulty, given B, sorry, which is the design is faulty, times the probability of B. What did I go to? Sorry. Excuse me. Where did I get to? Where am I? What is this? Sorry about this. Here we are. Okay. So we now plug in those numbers into the formula. Sorry about that. And you get the denominator is the probability of A, the probability of A given B, which happened to be this number, and the probability of B was 0.01. Okay, and that's 0.9870. So basically, because the chance that the house collapses, given that it's faulty, is so high, the chance that the design is faulty is actually quite high if the house collapsed. So again, one would expect a result of this type, even if one doesn't know the numerical value beforehand. Example 2. So this one's the insurance claims. So an insurance company believes that people can be divided into two types, which are basically accident-prone and those aren't. Okay, so that's our partition immediately. Their data tells us that an accident-prone person will have an accident at some point within a year with probability 0.04. It depends on what the accident is, but it's quite high. Whereas if you're not, then you have half the chance of that occurring, 0.02. Now, we are told that 30% of the population is accident-prone. Okay, so we're asked two questions. The first one is, what is the probability that a new policyholder will have an accident within a year of purchasing the property? We'll go back to part B afterwards. Okay, so let's formulate this. So let B be the event that a new policyholder has an accident within a year of purchasing the policy. And A1 and A2 are the events that a randomly selected new policyholder is accident-prone and non-accident-prone, respectively. Okay, so of course A1 is equal to A2 complement and vice versa. They partition the state space, and we know that the probability that an individual is accident-prone is 0.3. Okay, so the probability of A2 is 0.7. And we also know the probability that that individual has an accident conditional on them being accident-prone is 0.04, and the probability that an individual has an accident given that they are not is 0.02. So that's the information that's given to us in the question. What we want to compute is the probability that a new policyholder will have an accident within a year of purchasing. So I want the probability of B. Okay? So the probability of B is the probability of A1 multiplied by the probability of B given A1 plus the probability of A2 plus times the probability of B given A2. Okay, these are the numbers we just worked out. This one's 0.3, this is 0.04, this is 0.7, this is 0.02, gives you 0.26. Part B, if a new policyholder has an accident within a year of purchasing the policy, what is the probability that he or she is accident prone? So, okay, so that's asking clearly for the probability of A1 given B, okay? B is the chance, is the event that I have an accident. A1 is that this person is accident prone. Okay, so now I just apply the Bayes rule. Okay, so the denominator I've already computed. I don't know why we do it again. Probability of B is 0.26. The probability of B given A1, that's 0.04. The probability of A1 given A1, sorry, is 0.3. So that's the numerator. The denominator is just this one, and you get 6/13. Okay. Very good. Example 3. So example 3 actually is a lot more work, this one. You can have a look at the solution. No, this is not the one. It's a lot of work. Okay, that's fine. Example 3. So we have 3 cards identical in form, except card 1 is colored on red. Is red on both sides. Card 2 is black on both sides. And the third one is red on one side and black on the other. Okay, the 3 cards are mixed up in a box, and 1 card is randomly selected. So the idea is you're not able to see what the card looks like, and you put it down on the table. Okay, now the card is placed on the table. You can see the top of the card, and it happens to be red. We're asked, what is the probability that the other side is black? I.e., what is the chance that I pick the third card in my sequence? Okay, so, and it so happens that it's 1/3, right? You can see the solution. In fact, it's intuitive, right? We're going to compute this. You can guess that it's 1/3 immediately, but you can justify it in this following way. So we define AI to denote the event that card I is chosen. So A1 is the card which is red on both sides, A2 is the card that's black on both sides, and of course the same for A3. And B denotes the event that the upper side of the chosen card is red. So I know that B has occurred, by the way. So now we know the probability that I choose one of those three cards is equally likely, right? I just draw it at random from a box. I don't know which one I'm picking. Now, we know that the probability that the upper side of the card chosen is red if it's A1, so A1 is red on both sides, so that's got to be 1. The probability that it's red on the top, given I chose card 2, that's got to be 0 because that's black on both sides. And similarly for the third one, it's 1 upon 2. Okay. So now what we're asked to work out, so the desired probability is the conditional probability of card 3, but I want to compute the P of A3 given B. Okay, you can read the sentence. Okay, because I know that the card has red, that's B, and I want to compute the probability. It was the third one. So that's the probability of A3 given the probability of B given A3 over the this one here. This is just the probability of B, and that, remember the A1, A2, and A3 partition the sample space. They can't occur simultaneously. So the numerator, that's a half times a third. The denominator, well, these are all 1 upon 3. The first one is a 1, the second one is 0, and the third one is 1 upon 2. So that's what that sum is. And you get 1 over 3. You could have guessed that, I suppose, but this is a nice justification for that solution. Okay, so example 4. So this one's actually it's quite useful. This is a common example of Bayes' theorem. So you're told that only 1 in 1,000 adults is afflicted with a rare disease. I don't know how rare that is, but it's relatively rare. And there is a diagnostic test, which means that an individual can go into a hospital or something like that, and they can conduct some sort of medical test. And that test occurs, and if the individual actually has the disease, they're going to get a positive test with very high chance, 99% of the time, or probability 0.99. And now, if you don't have the disease, but you take the test, there is a chance of a false positive. So basically, if I don't have the disease and I come out with a positive result, that can happen 2% of the time. If that can never happen, it's a kind of boring question. But as one should know, that basically medical diagnostic tests are not foolproof. Now, what are we asked? Now, we're asked if a randomly selected individual is tested and the result is positive, what's the probability that they have the disease? Okay. And one would think that that should be quite high. In fact, the answer is, quite low, sorry. Okay, so we're given the formulation. So A1 is the individual has the disease, A2 that the individual doesn't have the disease, and of course that partition to space, and B is the result of a positive test. And of course what we're asked for is the probability that the individual has the disease given that the test is positive. So I want the probability of A1 given B. Okay, that's the same as the probability of A1 multiplied by the probability of B given A1 over the same thing plus this one, and this is because this is the probability of B because A1 and A2 partition the space. Now, the probability of B given A1, that's 0.99 because that's where I get that number from. The probability of A1, that's the chance that the individual actually has the disease. We know that's 1 over 1,000. So that's that number here. The denominator, well, this is the same thing here. And this one, the probability that the test is positive given that they don't have the disease we know is 0.02. Okay, that's what we say here. And the chance that they don't have the disease is quite high, 0.999. Okay, so we plug those numbers into this formula and you get 0.0472. Okay, so the chance is quite small. It's kind of funny, but anyway, that's what is. Okay, I don't think this tree diagram helps you at all, so we're going to move on. Example 5. I looked at it extensively before I came in, and I couldn't really see any benefit. Okay, example 5. So a student answers a multiple choice examination question that offers four possible answers. Okay, and the probability that the student knows the answer to the question is 0.8. The probability that the student will guess is 0.2. Now we assume the following. If the student guesses, the probability of getting the right answer is 0.2. 0.25, right? So they have no idea, so they say, okay, it's just going to be A or B or C or D or something like that. If the student guesses correctly, if the student correctly answers a question, right? So you're told that he or she has got the answer right. What's the probability that the student really knew the answer? Okay. So there's a chance that they got it right by pure guessing, but there's a chance that also they knew the answer. So the formulation here, we introduce three sets, A1, A2, and B. A1 is the chance that is the event that the student knows the answer. A2 is the event that the student doesn't know the answer, and that's of course a complement to A1. And B is the event that the student correctly guesses. Answers correctly, sorry. So what we want is the probability that the student knows the answer given that they have correctly guessed, or correctly answered, excuse me. So that's the probability of A1 times the probability of B given A1, and then, of course, A1 partition the sample space, and that's the probability of B by the law of total probability. So what are the numbers? Well, probability that the individual knows the answer is 0.8. That's what's given to us there. The probability that they answer correctly, given that they know the answer, is 1, right? Because if I know the answer, I'm going to answer correctly. That's the assumption, anyway. The concept isn't that even if that individual knows the answer, he's going to give the wrong answer. That won't happen. Okay, so that's the same denominator. And then the last one, the probability of B given A2 times the probability of A2. So A1 and A2 form a complement. So this is 0.8, this is 0.2. Now here, this is the probability that they get it right, given they're guessing, they don't know the answer. So this is 0.25. That's exactly what he is alluded to in the question. Okay, plugging those numbers into the formula is 0.94, right? So it's, what this says is that basically there was a good chance that the individual knew the answer. Okay, very good. Question 6. Example 6. Okay, we will do example 6 and then we will have our break. I'm beginning to get a bit tired of these examples, as I'm sure you are. Example 6. So you have components of a certain type are shipped to a supplier in a batch of 10. It's important to know that it's 10, otherwise we're going to have trouble. Now we suppose that 50% of all such batches, they have a defective component. 30%, no defective component, okay? 30% have one defective component and 20% have two, right? So basically you get a batch of 10, 0, you get everything's working with probability 0.5, you get one defective component with probability 0.3, and you get 2 with probability 0.2. Okay, and that's the worst case scenario. Now, what do? I've got my batch, I take 2 components out at random, okay, and I'm asked the following. What is the probability associated with 0, 1, and 2 defective components being in the batch if neither tested component is defective? Okay, so what that means is I put my hand in this batch, I've taken 2 out if they're small enough to take out. Okay, now what I found is that I've tested those 2 components, they're not defective. I want to know the chance that the number of defective components is either 0, 1, or 2. Okay, and of course one expects the chance of 0 to be reasonably high because I didn't pick up any defectives. Okay, so let's introduce some notations. AI is the event that I defectives are in the batch. Okay, so I ranges in the set 0, 1, and 2. Why? Because I can only have 0 defects, 1 defect, or 2 defects. Okay, that's that. DI is that there are I defectives in the sample. And again, the number of defectives in the sample that I take, that can be either 0, 1, or 2, because I only take out 2 things, right? I'm only taking out 2 batches. So the worst case scenario is I could get 2, I could get 1, or I can get 0 is also a possibility. Okay. Now, what's the probability that there are I defectives in the batch if I take I is equal to 0? Well, I know that because 50% of the batch has no defectives. Similarly, the probability of A1 is 0.3 and the probability of A2 is 0.2. Okay? Right, now what do I want to do? Now this has some combination parts in this, because in order to compute my probabilities, I have 10 things and I'm taking 2 out of them. So I have a combinatorial issue here. So basically the number of ways of taking 2 out of 10 is 10 choose 2. right? We don't care about the ordering. The permutations are not there. So there's 45 possible combinations of items I could have taken. Okay. Right. Now, what do I want to compute? Right. At the end of the day, I want to compute. So I'm going to go through the solution, but let me tell you what we want to compute. What we want to compute is the probability of A0 given D0, A1 given D0, and A2 given D0. So this event is the probability that, given that I drew 0 defectives, the chance that there are exactly no defectives in the batch, given that I drew 0 defectives, I got 1 defective, 0 defectives, 2 defectives. Okay, so now how do I compute those probabilities? Okay, so what do I want to do? So in order to compute those probabilities, I want to work out what is the chance of D0 given A0, and D0 given A1, D0 given A2, and so on and so forth. That will give me the probability of D0 using the law of total probability. So let's first of all think about this one. So just keep in your mind that what I'm trying to do is I'm trying to compute this one. Of course, there's no intuition given to you precisely at this moment of why you want to compute this, but because I have told you that this is the things we want to compute, and we're on course in the land of using Bayes' theorem, we want to compute this denominator. So that's why we're doing this. And this formula is the one we're using, because remember that A0, A1, and A2, they partition the state space. Remember that these probabilities sum to 1. I either have 0, 1, or 2 defectives in the batch. Okay. So now I'm asked the probability that I have I've drawn 0 defectives given that there are no defectives in the batch. Well, I don't have to do anything there. That chance is 1. If there's no defectives in my batch, I can't draw anyone out, so this is going to be sure, right? That's got to be 1. Now this one's a bit more difficult, right? Now I'm asking the probability that in my batch of 2, I draw no defectives, but there is 1 defective in my 10. Okay, so what do I do? So the number of ways I can draw no defectives from my batch of 10, there are 9 which are working, so there's 9 choose 2 possible ways of choosing the non-defectives, right? This one doesn't matter, it's 1, and then there are 45 possible ways of choosing 2 from 10. So then basically this is 9 choose 2 over 10 choose 2. Okay, that basically goes back to what we did in the first week. Similarly, if I want to compute the probability of D0 given A2, so in this case I have 2 defectives. So in order to draw no defectives, basically there's 8 choose 2 possible ways of doing that, and then there are 10 choose 2 possible ways of drawing things. So this is 0.622 is the chance of D0 given A2. Okay, so now what do? I plug in those 6 numbers that I've just computed into, this formula here. Okay, so the probability of A0, the probability of D0 given A0. Okay, so this is 0.5 times 1, and all these numbers is the ones I've explained here. Very good. So I'm almost concluded for this part of the lecture. So now what do I want to compute? I want to compute the probability of A0 given D0 first. So I apply the Bayes' theorem. That's the probability of A0 times the probability of D0 given A0. This one I know, it's 1, this is 0.5, this one I know. I get 0.5784. So these ones are exactly the same. For this one, the denominators are all the same. It's apparently 0.8664. And so for this second one, A1 given, I do 0.2, 0.622. This is A2 apparently, sorry. And A1 is 0.3, 0.8. And so that gives us our 3 solutions. Okay, so it's okay, so let's resume. So this is our last example. Actually, it's not very clear statement of Bayes' theorem, but it's a very popular problem which they used to. I don't know if they still do. They used to ask a lot on it in interviews for various jobs, and well, I used to be finance when I was young. I don't know if people still do those jobs or care so much, but anyway. So the question is this. It's actually a non-standard statement. Suppose you're on a game show and you're given the choice of 3 doors. Behind one door is a car, and behind the other 2 are goats. In fact, this is a little bit strange because you may be in the world where goats are more useful than cars, but let's suppose that you really want the car, but you don't want goats. Okay, that's the proviso. Normally, the statement of this question, there's nothing behind the other doors, which is more reasonable because often you prefer to have a car over nothing, because at the very worst you could sell it for something. Okay, so now you've got 3 doors. You pick number 1. And it's called the Monty Hall problem because the host is called Monty Hall, presumably. And so what that individual does is Monty is a man, so in this case, so he goes behind, he knows where the prize is, he knows where the car is, otherwise this is a kind of funny exercise. So this individual knows what's behind the doors, and he goes and opens the 3rd door, and he shows you it, and it happens to be a goat, or in most cases nothing, and he asks you the question, do you want to pick door number 2, or you want to stick? So you have 2 options. You can stay where you are, and then he will open the door, and there might be a goat behind it, there might be a car, or he'll go to or the true prize is behind door number 2. Okay, so there's just one thing you want. So the question is, do you want to stick or you want to switch? And there are a lot of answers to this. Generally the answer is switch, but let's have a look at this. So let's look at this from a probabilistic perspective, and this is a model for constructing a solution. There are many ways to answer this question, actually. So, the strategy 1, I stick. Okay. So I choose I choose the door with the car. I have no idea where it is. So with equal probability, the car is behind one of those 3 doors. So the chance that I choose that door is probability 1 upon 3. Now, Monty Hall is a game show host. Obviously, there's no fun to him opening the door for which the car is behind, because if he does, he's giving you the answer and it's game over. So he's a showman. So he's always going to open one of the 2 doors which has a goat behind it, right? Because if you've got the answer right, they both have goats behind them. If you got it wrong, one of them has a goat behind them. So he can always have that option. So if I don't switch, I'll win. Okay, so that's in this scenario. This scenario is I've chosen the door, the car is really behind it, and that happens with probability 1 upon 3. Okay, so if I don't switch, I stick where I am, I'll win if the car is really behind the door that I've chosen. In the other scenario, I choose a door where the goat is, okay, and then that's with probability 2 over 3. And in this case, I'll always, if I don't switch, I lose. So if I stick where I am, in this case, I lose. So the chance of winning is with probability 1 upon 3. I chose where the car was, and I stay where I am, so I got it right. Or in this situation, I got my answer wrong and I stayed where I was. So the chance of winning is 1/3 in this strategy. This is one strategy, by the way. Strategy B. Strategy B is I'm going to switch. So strategy B is I choose a door with the car initially with probability 1/3. Monty is always going to choose the open door with a goat, so if I switch, I lose. Why is that? Because in this, I chose the car initially, I got it right, but now I'm switching, so obviously I'm going to end up with the wrong answer. So this is with probability 1/3, I lose. I choose a door with the goat initially, okay, that's with probability 2/3, that's a much higher chance. Monty's always going to show me the goat, so if I switch, I'm going to win, right? Because I got it wrong. He'd shown me the one that's goat. I know that that's not an option. Obviously, I don't choose the door that Monty's opening, which has a goat behind it, because I don't want the goat. Otherwise, I'm going to get the goat. So if I switch, I win. Okay, in this case. So the chance I'm winning is 1/3 times 0 plus 2/3 times 1. 2/3. So basically what this says is, in the case where you choose to switch, you're twice as likely to win as whether or not if you choose to stick. Okay, this is a particular solution. In fact, there are many I don't think you were confused. I don't think anyone's confused with that solution. I think that there's some logic to that answer. But there are other strategies. If you want, I don't know if these links still exist, but I'm pretty sure you could just type in Monty Hall into your favorite search engine, or to YouTube if you like, or whatever engine you like using. You'll see lots of things about Monty Hall. Okay, and like I say, the solution is kind of subjective. There's lots of things you can do in this scenario. They like asking that in They used to like asking that in interview questions because there's a so-called open-ended solution, and people want to understand your logic when using probability. So, for example, this one is a valid solution, right? Is it right? Well, it depends on your model. Okay, so that was, I guess, light entertainment. There's not really Bayes' rule there, actually, but in fact, there is a way to apply Bayes' rule here as well. So we now move on to the notion of independent events. In fact, this is something seldom coming along so late in a probability course. Normally independent events are put towards the start of a course because I think they provide a nice way to understand things. But basically, well, we're going to see an example, but before we see an example, let me tell you what this thing is, at least conceptually. So an independent event, or a pair of events A and B, are independent if basically the outcome of the event A does not affect the outcome of the event B. And that's basically what it means. You can have multiple events as well, but and of course we'll formally define it. But that's where we're heading. So now we take the following. So we take a fair die and we roll it, and we define two events, A and B. A is the event that I'm going to roll it twice, sorry. The first event is that the first roll shows an even number, and the second event is that the second roll is a 5 or 6, right? So this is a fair die, and so intuitively, just from what I've been saying, one does not expect the outcome of the first roll, to influence the outcome of the second roll, just from using intuition. Okay, so now if we use the logic that we've been doing, right, which is basically we work out the possible number of total outcomes, and then we work out the number of times the possible event could occur, and we take the ratio as the probability, then we have the following procedure. The total number of outcomes, of course, is 36 if I roll twice. So the number of the outcomes of the event A, right? So in the event A, my first roll, I have to get an even number. So that's 3 choose 1 possible ways that can happen, right? And then the second one, I don't care what happens. So there are 6 ways that can happen, right? I can get 6 choose 1. It doesn't matter what I get on my second roll. So the probability of A occurring is 3 over 6, or 1 over 2. Okay, similarly, if you do the same for B, so for B, the second roll has showing a 5 or a 6, so that's 2 outcomes. So there's basically 2 times 6 choose 1, because I don't care what happened the first time out. On the bottom is 36, that's 1 upon 3. And the probability that A and B occur simultaneously, well, that's equal to the total number of ways that I can get an even number in my first roll, that's 3 choose 1. And then here I had to get a 5 or a 6, so that's 2 choose 1. And then I have 36 on the bottom, so that's 1 up over 6. Okay, so that's what I've been doing so far. Okay. Therefore, in this situation, if I'm interested in the probability that A occurs given that B occurred, so I'm told, it's rather non-intuitively, that the second roll shows 5 or 6, and I'm asked what's the chance that the first roll showed an even number. So intuitively I don't think that B should affect A, right? And so in this case that's the probability of A and B over the probability of B. The probability of A and B is a sixth, the probability of B is a third. On the other hand, okay, it's very exciting, I'm getting anywhere yet, the probability of A is equal to a half. Okay. So what does that tell you? Well, the information that the second roll was 5 or 6 has not changed the probability that A is occurring, right? I told you B happened, I got a half, but this one says the probability that A occurs was already a half. So this has brought me no additional information, and intuitively it shouldn't. Why should it be that if I got a 5 or 6 on my second roll, that influences the chance that my first roll I got a 2, 4, or 6? It shouldn't. It doesn't make no sense. And so that's what we're trying to get at. So in this situation, the probability of A given B is equal to the probability of A. Similarly, you can do the same calculation for B. It's the same thing. So in this case, both the conditional probabilities are equal to the marginal ones. That is to say, the probability of B given A is equal to the probability of B. The probability of A given B is equal to the probability of A. And what that really means is that A and B are not influencing each other as we expect. We know the following. So in general, the probability of B given A is not equal to the probability of B. Okay, one can easily find an example. If you look through your lecture notes, you can easily find that. Probably we've seen at least 5 or 6 examples today. So that is to say, if you tell me, so just as I said, so I'm ahead of these notes, if you tell me that A occurs, that should affect the probability of B occurs in most cases, because basically there may be some influence. But this is a special case, right? And the special case is that essentially A is not influencing B. And we have a formal way to define this. So we say that two events A and B are said to be independent if the probability of their intersection is equal to the product of the probability of A and the probability of B. Okay? If the two events A and B do not satisfy this equality, then the events are said to be dependent. Okay? And that's simply that. Okay. So, what does that mean? So I hope we're going back to our example. No, we don't. No. We go back to our example. So in this situation, the probability of A and B is precisely, so let's have a look in our example. Sorry. The probability of A and B is a sixth. Okay, the probability of A was a half. The probability of B is a third. A third times a half is a sixth. A and B are independent. Okay, and that means the event A does not influence the event B. Okay, that's what we think of it, and that's how we think of it. And this is actually a much easier way to compute probabilities. Never in my life would I do this calculation to get the probability of A and B, right? Because the probability of A and B is simple. I know that if I roll a fair die and I roll it again, unless there's some kind of wind conditions, some funny things happening, basically I'm expecting the roll of the first die to not influence the roll of my second die. So I know the chance that this one occurs, that's equal to a third. I know that this one occurs is equal to this one's equal to a half. This one is equal to a third. The probability of their intersection is equal to a third times a half. And I would never do one of these calculations. And this is why the concept of independence or understanding independence is very useful, because it saves us from this kind of almost nonsensical calculation. It's very much easier to do it just by using the fact that they're independent. In this case. Okay. So that's what. So as I've said it like 4 times, that first bullet point summarizes what I've just said a few times. There is some kind of important things to note. So A is independent of B. So if you don't know what this thing means, I'm sure you do. This means if and only if. So that means A is independent of B implies B is independent of A, and that means that this. So that's this way. And B is independent of A implies A is independent of B. Okay, that's what if and only if means. Okay, and so this thing is true if and only if the probability of A and B is equal to the probability of A times the probability of B. Okay. Hopefully this causality of those if and only if statements are clear from the definition. Okay. Suppose that, so let's have a look at some implications, some properties of independent events. Suppose that we know the probability of A and the probability of B is simultaneously non-zero. If A and B are independent, then the probability of B given A is equal to the probability of B, and the probability of A given B is equal to the probability of A. Does he show it? It should be pretty obvious. So why do we need this blue statement? Well, the blue condition is needed precisely because in order to define a conditional probability, we need that the probability of the event that I condition in on to be strictly positive. And so then basically how would I obtain this formula? How would I obtain this equality? Well, you know that the probability of A and B is equal to the probability of A times the probability of B. So the probability of B given A is the probability of A and B over the probability of B probability of A, sorry, so that probability of A and B over the probability of A is precisely the probability of B. Okay, you just apply simply, so if you are not listening to me, I apply this definition in the formula for this thing. Okay. And this is exactly what we saw in our example, I think. Yes. Okay. Now, the second property that we investigate. Suppose that the probability of A and the probability of B is strictly positive. If A and B are independent, A and B cannot be mutually exclusive. Okay? So remember, what does it mean for A and B to be mutually exclusive? Well, it means that if I take the probability of A intersect with B, that's equal to 0. Okay, that's because basically the intersection of A and B is null. The probability of the null or empty set is exactly equal to 0. Okay, so this is the statement. So I'm saying this is the case. Then if A and B are independent, they cannot be mutually exclusive, and the proof is clear. Okay, the probability of A and B is equal to the probability of A multiplied by the probability of B. Okay, by construction, this product on the right hand side is strictly positive. This number is positive, this number is positive. I multiply two positive numbers by each other, I still get a positive number. Okay, but if they're mutually exclusive, this thing on the left hand side, it must be equal to 0. And so this is of course a contradiction in the sense that if I was mutually exclusive, I can't have this. Okay, because the probability of A and B must be equal to 0 if A and B are mutually exclusive. So therefore, A and B cannot be mutually exclusive if they're independent and we have this condition. Okay. So, and we can say the converse in this situation. So the probability of A and the probability of B are both positive. If A and B are mutually exclusive, then A and B cannot be independent. It's essentially the same way to prove this. This is pretty straightforward. If A and B are mutually exclusive, then the probability of A and B is equal to 0. On the other hand, the probability of A is positive, the probability of B is positive, the probability of A times the probability of B is positive. This is 0, this is positive, this one cannot be equal to this one, therefore they cannot be independent. Okay. Okay. For the sample space S as well as the empty set phi are independent of any event. Okay, we can also show this thing. So how do we show that? So for any event A intersection S is equal to A. We know that already. And A intersection with the empty set is also the empty set. Now the probability of A, therefore the probability of A and S is equal to the probability of A, right? Because A and S is equal to A. The probability of A is equal to the probability of A times the probability of S, where the probability of S is equal to 1. So therefore, the probability of A and S is the probability of A and times the probability of S. Hence, S is independent of any event. A is arbitrary. Similarly, the probability of A and phi, well, the intersection with A and the empty set is the empty set. So the probability of the empty set is equal to the probability of the empty set times the probability of A, because this is 0. Alright, so it doesn't matter whatever crazy rubbish I put here, just as long as there's a number between 0 and 1, I still get 0. So then, because basically the probability of A and phi is equal to the probability of A multiplied by the probability of phi, the phi is independent of any arbitrary event A. Okay, property 5. If A is contained in B, that is that everything that's in A lies in B, and A and B, then A and B are dependent unless B is equal to the sample space. Okay, how do we prove this? So A contains in B means the probability that the intersection of A and B is equal to A, because every element of A lies in B, but B may have some extra elements. Now the probability of A and B, hence, is the probability of A, and that's not equal to the probability of A times the probability of B, unless the probability of B is precisely 1. And that implies that B is equal to S. So basically A and B are dependent. Okay, some remarks. We'll make some remarks. There are a few more remarks here, and we'll see a lot of examples, I think. We have plenty of time. So the properties of independence, unlike the mutually exclusive property, you can't really show them on a Venn diagram. And I don't show many things on a Venn diagram because basically when you learn probability in math, and I'm someone who studied mathematics, you are always told that Venn diagrams prove nothing. Okay, indeed in this situation they don't really help you at all. So basically, and it should be stressed that if you are trying to understand independence, one must use the calculations as set out in these previous examples. You cannot use a Venn diagram. Okay, if you try to establish that two events are independent and you put in an event and you start using Venn diagrams, you're going to get very confused. And in any examination, anyone who grades it, and I don't grade everything, but if I'm grading it, I'm going to give you 0 because you cannot do anything with that. So keep that in mind, please. Mutually exclusive events are dependent events, right? Because the probability, yeah, okay, so we already know that. Okay, so let's make some more remarks. So mutually, oh goodness me, yeah, there's a lot of remarks. Okay, so bear with me. Mutually exclusive, I don't know, maybe my colleague found that students got mutually exclusive and independent confused a lot. So let's see a lot of examples about this. So mutually exclusive events and not independent events. Okay, let's understand this. So we take the event A, the event of odd numbers. So I roll a die, I get odd numbers 1, 3, 5. D is the event of even numbers 2, 4, 6. A and D are mutually exclusive because if I take the intersection of A and D, of course I get the empty set. The probability that A occurs, well, that's equal to 1/2. The probability that D occurs, that's equal to 1/2. But the probability of A and D is equal to 0. The probability of A times the probability of D is 1/4. The probability of A and D is equal to 0. So A and D are not independent. So this is an example where A, the event A, and the event D are mutually exclusive, but they are not independent. Okay? Hopefully that's clear. Not mutually exclusive and not independent. Okay, let's have another example. So here I roll a die again. Throwing and rolling are the same thing, by the way. So we have the event A, that you roll an odd number. The event B, which is the event, the numbers that I roll is at most 3. So I get a 1, 2, or a 3. Okay? So the intersection of A and B is clear. It's the set 1 and 3. So I can get a 1 and 3, I get a 1 and 3. Okay? So A and B certainly are not mutually exclusive because their intersection is not empty. The probability of A occurring, well, that's 1/2. The probability of B occurring is 1/2. The probability that they both occur is 1/3. Okay, so if I multiply this by this, that's equal to 1/4. This is 1/3 because there are two events which are equally likely. So basically, in this case, A and B are not mutually exclusive and they're not independent. Okay, so now I have a pair of events. They're not mutually exclusive, but they happen to be independent. Okay, I think that this distinction is becoming clear. I think what happened is my colleague had a 1 year where he taught the course and the people were getting confused between mutually exclusive and independent. So I hope that this is a kind of clarification between those things. Okay, so I roll a dice. I have A, which is the event of an odd number, and C, which is the event that my number is less than or equal to 4. Okay, so I get 1, 2, 3, or 4. The intersection of A and C, well, that's a 1 and a 3. Okay, so A and C certainly are not mutually exclusive because the intersection is non-empty. The probability of A occurring, well, that's certainly 1/2. The probability of C occurring is 2/3 because that's 4/6. So the probability of A and C is equal to 1/3. Okay, so the probability of A times the probability of C, well, that's 1/3. The probability of A and C is equal to 1/3. So A and C are independent. So they're not mutually exclusive, but they are independent. Okay, good. So let's have a look at some examples. There are a lot of examples. I think that some of them are quite neat. I think some of them are less exciting. So the first one is the following. It's pretty straightforward. So I have the probability that a person makes a mistake on their state income tax return. I think this is income tax in Singapore. There's only one state. Is 0.1. Okay, and we're asked to find the probability that two totally unrelated people make a mistake. Okay, so basically what this means is you take person A on side A of the island and you take person B on side B of the island. They've never met, they don't know each other, they have no friends in common, nothing at all. So basically the chance that they make a mistake is basically the same and is independent of each other. So the chance that they both make a mistake is just the product of the two probabilities is 0.01. Okay, M1 and M2 is the person I makes a mistake. There are two people. So I take the product, that's 0.01. Okay, an example of two independent events. Okay, there's a theorem. Okay, the theorem we're not going to prove, although you can find the solution easily in any probability textbooks. We don't do many proofs other than the ones we've seen. The result is the following. A and B are two events and they are independent. That means that the probability of A and B is equal to the product of A times the product of the probability of A times the probability of B. If that's the case, then A and B complement are independent, A complement and B are independent, and A complement and B complement are independent. So once you know that first property, you know a lot more. Okay, you can check actually if you want. You can work out the probabilities. It's not important to be able to prove it right now, but we could if you liked. Okay, example 2. So the example is the probability that Tom will be alive in 20 years is 0.7, it's a bit morbid. The probability that Jack will be alive in 20 years is 0.9. And we're asked the probability that neither of them are going to be alive in 20 years. So kind of interesting, I guess. Okay, so basically we know the chance they're going to be alive. We know the chance that, so what we want to know is that in this case where they're both independent, because we're going to assume that Tom and Jack are friends in a common circle doing the same things, the same ages and so on and so forth. They're completely independent. So we're interested in the probability that Tom dies and Jack dies at the same time, okay, which is the complement of the chances that they survive. So the answer is 0.3 times 0.1. Okay, I'm sure that's the answer, yes. So let's look at the solution. If you like, let's formulate that properly. So A and B respectively are the events that Tom and Jack are still alive. And we're going to assume that they're independent. In fact, that's the only thing we can do given the information that we have. Okay, otherwise it's a model actually. He doesn't tell you that, but you can guess it. So because these two events A and B are independent, so are their complements. So the probability of A complement and B complement is the probability of A complement times the probability of B complement, which is equal to 0.3 times 0.1 is 0.03. Very good. Okay, so now that was two independent events. So I have A and B. I have the probability of their intersection is equal to the product of their marginal probabilities. This is also, one can define independence for n, a fixed but arbitrary number of events, A1 up to AN. So the definition is as follows. So I have n events, A1, A2 up to AN, and they are said to be pairwise independent. Okay, what that means is I take any pair of events, I and j, so A1, A2, A1, A5, A9, A11. I compute the probability of their intersection, and that's equal to the product of their probabilities. Note pairwise. This is only for two of the events. This is for any two, okay? But only two. Mutually independent means something else. Okay, so there's a distinction. Now I take the same n events. Well, let's say they're different. But anyway, I take n events, A1 up to AN. Now, they are said to be mutually independent, or you can use the phrase independently. This phrase and this one is almost always everywhere used exchangeably. Okay, so they're independent if I take any subset, so I1, I2 up to IK. That means basically K can be any value, 1, 2, 3, well 1 is a bit silly, but 2, 3, 4 up to N, and I take the probability of the intersection of this and they equal to their products. That means, what does this mean? It means if I have A1, A2, A3, A4, what that means is that they're mutually independent if I take A1 and A2 and the probability of their intersection is equal to the product of their probabilities. I take A1, A2, A3, and they're equal to the product of their probabilities. I take A1 and A4, it's equal to the product of the probabilities, and so on and so forth. For every, or any, for every might be a better way to say it, but basically, whatever subset of those I take, I get independence. Now note that, basically, as it says here, Yes. Basically, just make it, just remark, as I think there's an important remark immediately. Note that if I take A1 up to AN and they're mutually independent, immediately they are pairwise independent, because this condition here is a subset of this condition here. Okay, but clearly pairwise independence does not necessarily imply mutual independence. Okay, so these are two separate definitions. Okay, let's make some remarks. So when one says, okay, so let's clarify this statement. To me it was clear, but let's make it clear for everyone. If you say that A1 up to AN are independent, what it means is for any pair of events, basically I take that the probability of AJ intersection AK is the probability of AJ times the probability of AK. For any three events, the probability of AI and AJ and AK is equal to the product of 3, and for any n, this also occurs. Okay, so that's what it means. Okay, that's what I mean, I said that repeatedly, but hopefully that's clear now. As I said in head of the notes, that mutually independent or independence implies pairwise independence. Of course, the reverse is not true. Okay, another remark. I take A1 up to AN, they're independent. I define BI is equal to AI. Of course, the BIs are all independent. If I define BI equal AI complement, then the BIs are also independent. Okay. That's basically just repeating what it says in point 3. So let's have a look at some examples. We have 10 minutes. The first example looks harder than it is. So we had a fair die, so that means that each side is equally likely to land on any other. And if roll it 3 times. And I'm asked the following: what is the probability that the first roll gives an odd number, the second roll gives an even number, and the third roll gives a number greater than 4? Okay? So these are 3 independent events. It's fairly clear. So I define the following. So you can have a look at the solution, but I don't need the solution to give you the answer. So A is the event that you get an odd number rolled on the first toss, the first roll. Okay, so there's 3 possible outcomes, and that probability is a half. B is the event that an even number is obtained on the second roll. Well, that probability again is a half. I get a 2, 4, or 6. And this is I get a 5 or a 6. That's probability 2 over 6, 1 over 3. So I do a half times a half times a third, and I get my answer, which is what, 4, 12, 1 over 12. Okay, very exciting. And that's the answer, 1 over 12. So if you like, this page I think is unnecessary, but I think the point of this working out is to show if you use the combinatorial approach that we originated in the first part of the lecture notes, you would be spending a long time doing a very, very trivial calculation. All right? So as you saw, I just looked at this and I told you the answer. I didn't have to do any of these combinatorial things because I know the chance of the first event, the second event, and the third event. Okay? Because basically the mutual, I mean, yeah, I don't know that this really tells me anything. Yeah. Let's have a look at example 2, which I think is more interesting. So example 2. Now, this one is a bit different, and we have to do some thinking. So A is, we introduce the event that the first dice shows an even number. B is the event that the second dice shows an odd number. And C is the event that the 2 dice both are odd or both are even. So clearly A and B are independent, but C is a little more complicated. So the probability of A, well again I don't need to do any combinatorial equations, any combinatorial work. Basically this is a half, this one's a half, so that's easy. Now C is a bit more complicated. Basically now this one's the probability that both die are odd. Okay, now the probability that they're both odd is going to be a half times a half, so that's a quarter. This one's that they're both even, that's going to be a half times a half, that's a quarter. So a quarter plus a quarter is a half. Okay, so that's the probability of A, B, or C. Actually, the question doesn't ask you anything. It's not it's an example, but it's not a question, right? So it's telling you things. Now, in this situation, let's have a think about the probability of A and B. So the probability of A and B is pretty straightforward. The first die shows an even number, and the second die shows an odd number. That's straightforward. That's a half times a half, so it should be a quarter. Okay, there's nothing to do there. We know they're independent events. A and C, the first die shows an even number, and the two dice show on both odd or both even. Here we have to think a bit, which is not so obvious a priori that these are independent events, A and C. Okay. So for A and C, we do the combinatorial thing. So in the denominator, there are 6 choose 1 times 6 choose 1 possible outcomes, 36. This one, well, there are 3 choose 1 possible outcomes in the first one, right? I've got one even number from 3. And then this one, again, I have 3 choose 1 possible ways. So then it's got 1 over 4. So they happen to be independent. And the same, you can do the same game for B and C. B and C and A and C are the same calculation. So A, B, and C are all pairwise independent. But it's clear that A, B, and C are not mutually independent because the probability of A occurring and B occurring and C occurring is 0. Why is that? Because if A occurs and B occurs, C does not occur, right? Because this one says that I have to get both odd on both rolls or both even. Right, here I've got odd and even, so that can't happen. So, and of course the probability of A and B and C multiplied together is 1 over 2 to the power 3, which is not equal to this. So basically, A, B, and C are not mutually independent, but they are mutually exclusive. Okay, there's a small phrase there. Okay, let's have a look at example 3. We've just got 5 minutes left. I think hopefully the examples are kind of clarifying things. You have 3 fire engines, excuse me, they operate independently. The probability that a specific engine is available when needed is 0.9. What is the probability that no engine is available when needed? Okay, so this is straightforward. That's 0.1 to the power 3. Okay, let's have a look at the solution. Yes, very good. So the solution is EI. So we start with EI, which is the event that the ith engine is available when needed. Okay, and so the event that no engine is available is E1 intersection E1 complement intersection E2 complement intersection E3 complement. So E1, E2, E3 are independent, so therefore so are their complements. Okay, so the probability of EI is 1 minus the probability of EI complement is 1 minus the probability of EI is 0.1. Okay, so the probability of the event of interest is just the product of these probabilities, which is 0.1 to the power 3, as I told you. Okay, let's have a look. Oh. All right, well, luckily for us, we've got 4 minutes left. This is the last example of this. We're going to stop after this example, even if we're behind time. Because I didn't look at anything after this. So example 4, the probability that a grader will make a marking error on a particular question of a multiple choice question exam is 0.05. Now, if there are 10 questions and the questions are marked independently, it's a rather strange thing to say, what is the probability that no errors are made? What is the probability at least one error is made? And then we'll ask the last one at the end. So let's try it with A. So EI is the event of making an error on the ith question. So now what do I want? So now I'm assuming that E1 up to E10 are independent, and so therefore they're complements. So the probability of no error in any of these 10 questions is the probability of E1 complement and E2 complement ... and E10 complement. They're independent, so that's equal to the product of their probabilities. The probability of making an error is 0.05, so the probability of making something correct, getting it right, is 0.95. So there's 0.95 to the power 10, and it's that value there. Part B, what's the probability that at least one error is made? Okay, well there's a lot of way to do it. Hopefully it does it the easy way. The probability of at least one error is 1 minus the probability that there is no error in 10 questions. Well, we've worked that one out. That's 0.95 to the power 10. So the answer is 1 minus 0.95 to the power 10 is 0.4013. Okay, let's see part C. So now it says the following. Oh, this is just generalization. So if there are n questions and the probability of marking error is p rather than 0.05, give an expression in terms of np for part A and part B. Okay, but this is pretty straightforward, right? So this is 1 minus p to the n, and this is 1 minus p to the n. Yes. Okay, so how do I get these expressions? So this probability is 1 minus p here, so I get 1 minus p, but I multiply, instead of 10, I have n of them, so I get 1 minus p to the power n. This is the answer here. And in this question, this is 1 minus the answer I got before, so that's 1 minus p to the power n. Okay. And that's it. That's the end of chapter 1. Chapter 2 is what is in store for us tomorrow. What is chapter 2 about? Random variables. Oh, very good. This is now becoming more, this becomes more like mathematics than probability, really, but anyway. So that's it for today. Just to let you know that at the moment it looks like chapters 1 and 2 are the only things which are on the midterm. This is going to be confirmed with an email tomorrow by one of the lecturers on ST2334. So thanks very much for your attention. I see you tomorrow in LT28 at 2 o'clock. Thank you.